That covers the main ideas. Let's stop for a moment and gather what we learned about dynamic arrays. Let's review. A dynamic array is a small handle on the stack. It holds three things: a data pointer, a size, and a capacity. That handle owns one block of memory on the heap. This is the same idea as a vector in C++ or an array list in Java. Here you built it by hand. Remember size versus capacity. Size is how many elements you are using. Capacity is how many slots you have room for. The spare slots are paid for in advance. They give you cheap appends later. The rule is always true. 0 is less than or equal to size, and size is less than or equal to capacity. Append is fast when there is spare room. It just writes one value in big O of one time. When the block is full, it runs the resize steps. It calls realloc for double the capacity, and the data pointer may move. That step costs big O of n. Doubling is the key. Because we double, append is amortized big O of 1. Over n appends, the total copies stay under 2, and this was our first amortized argument. We use the very same idea again for hashing in chapter 13. Now the C lessons. Always write the safe pattern. Temp equals realloc, then repoint, so you never lose the block. Call free one time for each vector, and never keep an old pointer across an append because the block may have moved. Now think about one weak spot. Both the plain array and the dynamic array pay big O of n to change the middle. Every element after the gap must shift. What if we could add a new element by rewiring a single pointer with no shifting at all? That is the next chapter, singly linked lists. The nodes are spread across the heap, joined by next pointers, and inserting is just a pointer rewire.